Hello everybody and welcome to my presentation about the assessment of ammonia as a biosignature gas in exoplanet atmospheres. In this presentation I'd like to give you a small introduction about the topic, about ammonia, about biosignature gases and ammonia, what kind of source it has and what kind of sinks. And I'd also like to talk about the methods that were used in this study and the results, obviously. And also, I'd like to have a quick discussion about what are the problems that they face in this study, what was kind of forgotten, or let's see. And in the end, I'll give you a quick summary about what you just learned. So let's start. Just some basics. What is this study even about? Basically, it examines the potential of NH3 as a biosignature gas. And what are biosignature gases? Biosignatures are gases that are produced by living organisms as a final product or a byproduct from biochemical pathways. And it has some characteristics that it needs to have. For example, it must be distinguishable and detectable in spectral features. And it should be measurable in spectral features in the reflectable light of the planet, so we can detect it with our telescopes. Also, biosignature gases should not occur naturally in for life suitable temperatures or pressure ranges or through geophysical processes. So we actually know that it is a biosignature. Ammonia. You've probably already heard about ammonia a lot in chemistry class. It has a very high solubility in water and a very high biousability, and it is also a greenhouse gas. But its residence time in the atmosphere is less than a day, so I'll be talking about that a bit later. But ammonia also gets easily destroyed photochemically, which is also something you really need to know because I'll be mentioning that a lot. Ammonia is a biosignature. As I already told you, ammonia has a very high water solubility, and the atmospheric accumulation is highly dependent on the planetary conditions. So if there is a water ocean on the exoplanet, then it would be harder for us to detect if there's not enough NH3 production on the planet. So it really depends on that. Also, there's a lot of NH3 in the cosmos, so it might also be possible that there are liquid ammonia oceans out there on some exoplanets. And in terrestrial planets' atmospheres, ammonia is a very good biosignature gas because terrestrial planets have no significant known abiotic NH3 source. Now let's start with the ammonia sources. I already highlighted in picture 1 the 3 sources or ways of production that I will talk about. There's anthropogenic NH3 production, biological production, and there are also some minor abiotic sources. Let's start with the anthropogenic NH3 sources and the production of them. The most global emissions stem from anthropogenic NH3 production. For example, which you probably know about, is agriculture, where ammonia is used as a fertilizer. The emissions of NH3 of fertilizers heavily depend on the type of fertilizers, the local meteorological conditions, and the soil property. Another NH3 source is animal husbandry. And through microbial decomposition of animal waste, NH3 gets produced. Another one is coal burning, and you can also see that in picture number 2. There's a table with all of them listed and how much the global flux is. Coal burning has a very relatively small impact. Also, the global NH3 emission flux is very hard to estimate because the most measurements are local, and like I already said, the lifetime in the atmosphere of NH3 is less than a day, and the NH3 abundance varies. A biological source is nitrogen fixation, and that is when atmospheric N2 is converted to NH3 by diisotrophic bacteria and archaea. That is also highly energetically costly, and it likely originated very early in the evolution of life on Earth. So it has been around some time, and it dominates the biological production of NH3, which you can see in picture number 3. There, ammonia gets compared to other different gases, how much the production is a year. Another biological source is ammonification, where the organic nitrogen converts within organic matter into NH3 by microorganisms like bacteria or fungi, and the microbial decomposition of animal waste, which I already talked about, is one of the main processes contributing to agriculture flux of atmospheric NH3. The last one of the biological production of NH3 I'll be talking about is the dissimilatory nitrate reduction to ammonium, short DNRA, and which is basically a nitrate or nitrite ammonification, and that is basically an anaerobic chemoorganoheterotrophic respiration. And that uses nitrate, NO3-, as a final electron acceptor. So basically it's nitrate gets reduced to nitrite and then to ammonia, while organic matter is oxidized anaerobically. So now the minor NH3 sources. Lightning is one of them, and it only produces a really small amount in the atmosphere, as well as volcanic gases. That some volcanoes on Earth, not all of them, have trace components when they produce trace components when they erupt. The last way they can, or another way, not the last one, NH3 can be produced is photochemically, and that happens when iron-doped TiO2 containing sands get exposed to UV or sunlight, and that reduces the N2 to NH3 and has some trace N2H4. But that is only significant in arid or semi-arid regions, because mostly when there is vegetation, the nitrogen fixation gets used, and not photochemically in more sandy and Sahara regions, Sahara-like regions. The ammonia sinks. I already highlighted those. I'll be talking about again for you. There are atmospheric sinks and biological sinks. And some of the atmospheric sinks, there are two that I'll be talking about. One thing you need to know is that NH3 is highly reactive in the atmosphere. So NH3 will go into photolysis under UV conditions, which you can see in picture number 4. There are two ways where it will be produced, if that's right. So the end product of those two ways are either NH2 plus H or NH plus H2. And the other one you can see in picture number 5 is when NH3 reacts with non-radicals in the atmosphere. There are also biological sinks. Life is actually a very significant sink for NH3 because the NH3 gets used for nitrogen-containing organic building blocks for life. And there are also two ways that it gets used. One is by the process of oxidation of ammonia to NO3-, where NH3 oxidizing bacteria and archaea harvest energy by aerobic oxidation of NH3 to NO3- via a two-step process. The other one is anemox, and that is a process of anaerobic oxidation of NH3, where anaerobic chemolithoautotrophs convert NO2 minus and NH3 directly to N2. And that is responsible for 50% of marine production. Now I'd like to talk about methods and results. Basically, what you need to know is that NH3 can theoretically accumulate in the atmosphere with reasonable surface production flux, only when life is the net source of NH3 and produces enough NH3 to saturate surface sinks. Result number one that I'd like to talk about is that NH3's high water solubility limits its ability to accumulate in the atmosphere. So, as I already told you, the atmospheric accumulation of NH3 is highly dependent on whether there are active NH3 removal sinks on the surface, or like if the surface is already saturated. Rain limits NH3 accumulation in the atmosphere because it takes down the NH3 because it is so highly soluble, and takes them in the ocean, for example, so there is less NH3 in the atmosphere for us to detect. And NH3 is actually water soluble because it has the ability to form hydrogen bonds with water molecules. And as you can see in a previous study, they showed that ammonia, compared to other studied biosignature gas candidates, it has one of the highest water solubility. They calculated that with the Henry's law constant, and yeah, I already highlighted for you. You can see it has the highest, and when the Henry's law constant is high, that means that it's more soluble. Result number two is that NH3 can accumulate in atmosphere if life produces enough NH3 to saturate the surface sinks. They study that by using a simplified ocean NH3 interaction model, where the ocean pH and the planet's total NH3 reserve are in equilibrium without atmospheric sinks. And when NH3 dissolves in the ocean, it reacts with the water. And then NH4 plus and OH minus ions get produced. Life is the net source of NH3. And the NH3 production needs to be at 6 times 10 to the power of 18 mole to maintain the NH3 reservoir to reach a detectable level in the atmosphere on a planet where there is no sinks. And the detectable level has to be 5 parts per million, which I'll talk about in result number 3, why that is. Result number 3 is about the detectability of NH3 in transmission spectra. And they study the detectability and transmission spectra with the EAS code, and it shows that the detection of NH3 is possible using James Webb Space Telescope if the NH3 mixing ratio reaches 5 parts per million. And they tested that by comparing a simulated spectrum of with 5 parts per million of NH3 and a spectrum without NH3. And they found out that the spectrum with 5 parts per million had spectral features from 10 to 40 parts per million larger than the spectrum without the NH3. So they set like the minimum to the 5 parts per million that they need for a detectable level. They actually tested that on different dominated atmospheres, and they found that the H2 dominated atmosphere needed the 5 parts per million mixing ratio for James Webb Space Telescope to be able to detect it. And the other characteristic for this test that you need to know is that the exoplanet was orbiting an M dwarf star, and that this systematic noise floor from the James Webb Space Telescope is 10 parts per million. They also tested it on the N2 and CO2 dominated atmosphere, also like high molecular weight atmospheres, and they found out that the signal is way too weak to be detected by JWST. Result number 4 is about the I'm sorry, variability of NH3 atmospheric accumulation in various planetary scenarios. And they use a photochemically model to simulate the NH3 mixing ratio in various planetary atmosphere scenarios. One thing that they found out was the NH3 that can accumulate in the atmosphere with a reasonable surface production flux only when life produces enough NH3 to saturate the surface sinks. And the required biological surface flux to reach the 5 parts per million is 10 to the power of 10 molecules per centimeter squared times S for an exoplanet orbiting an M-dwarf star with the surface saturated and an H2-dominated atmosphere. So that is like comparable to the methane production on Earth. And the other side is that when the surface is unsaturated, it needs much more NH3 production so that the sinks are saturated, and then they came to the required biological surface flux. It came up to 10 to the powers of 15 molecules per centimeter squared times S. The other thing they found out was that the NH3 surface deposition has an effect on the atmospheric NH3 mixing ratio. So the mixing ratio is higher when there is no deposition because the surface deposition removes NH3 from the atmosphere. Now I'd like to talk about the problems and have a little discussion. The thing is that they forgot about the wind, or they didn't take it into account at first. So they had another simplified NH3 land-ocean transport cycle and model made, as you can see in picture 7. And the most important thing is that horizontal wind transport limits NH3 accumulation above land when the planet surface is unsaturated with NH3. Because when life, land-based life, produces NH3, the wind transports it over the ocean and into the atmosphere, where it can either rain down, where it gets dissolved in the ocean, or it can go up and gets destroyed photochemically. And the NH3 accumulation to a detectable level is limited because when it rains down, then it's not longer in the atmosphere. So we have less in the atmosphere, and when it doesn't reach the 5 parts per million limit for us to see, then we don't know it's there. I mentioned in the minor NH3 abiotic sources that lightning might be also one of them, or is one of them, but it's not likely an efficient source of NH3 because in oxidized atmospheres, there's very low concentration of H-constraining reductants. And so it's not really likely for lightning to be an efficient source. Another important thing that I also like to talk about is the volatile amines, and that they're a very good biosignature gas because they are very similar to NH3. They have similar solubilities and reactiveness, and they show similar features in their infrared spectra. You can see in picture 8, I already highlighted the amines and the ammonia for you. That's also, again, with Henry's last constant with the solubility in water, that the ammonia and the volatiles have a higher solubility, and that they are similar to ammonia. I already told you that the NH3 is a greenhouse gas, but the greenhouse effect of it is negligible on Earth because the higher reactivity and the short atmospheric lifetime. And what I found interesting that on an H2-dominated atmosphere, the NH3 does not lead to a considerable increase in the surface temperature, but on N2 and CO2-dominated atmospheres, it could heat the surface significantly. Another problem is that we need better telescopes and more telescopes to do more studies on that and have more telescope to look at possible exoplanets and to see if there is ammonia on some of them. And because the James Webb Space Telescope or telescopes like it can only characterize exoplanets transitioning M dwarf stars and orbiting in a habitable zone, and those with H2 dominated atmospheres within a reasonable observation time. So we need more and better suited telescopes for the hunt for ammonia. Another problem is that NH3 also exists in mini Neptunes because mini Neptunes also can produce NH3. So the problem here is that any detected NH3 might get considered as a possible biosignature, which you should not. So the future outlook, I talked about that we need more and better telescopes for it. So good news. The Origin Space Telescope from Caltech will constrain atmospheric composition, and with the far and mid-infrared spectrometer that it has, it will be able to detect ammonia, which is really cool. Now we'll get to the summary. Your take-home message. NH3 in a terrestrial planet's atmosphere is generally a good biosignature gas, because terrestrial planets have no significant known abiotic NH3 source, and NH3's high water solubility and high biousability likely prevent NH3 from accumulating in the atmosphere to a detectable level, unless life is a net source of NH3 and produces enough NH3 to saturate the surface sinks. When exoplanets with H2-dominated atmospheres orbit an M-dwarf star, the 5 ppm, 5 parts per million mixing ratio is needed for NH3 to be detectable with James Webb Space Telescope, considering the 10 parts per million James Webb Space Telescope somatic noise floor. Also, something I'd like to highlight is that the volatile amines share NH3's weaknesses and strengths as a biosignature. And to establish NH3 as a biosignature, we must rule out mini Neptunes with deep atmospheres where NH3 can be produced because of high temperatures and pressures. Those are my sources. Thank you so much for listening and watching. Please leave your questions in the comments.